The term redox stoichiometry puts a lot of dread in people. Individually, each of these words are their own topic, but when you put them together, things seem to get a little bit harder. But bear with me, this topic isn't as hard as it seems. From previous studies of chemistry, you probably remember that stoichiometry is all about the molar ratios and things like that, whereas redox is about electron transfer reactions. When you put these things together, you end up doing calculations. Basically, this is all about calculations and calculations relating to electron transfer reactions. The key components of a redox stoichiometry equation is, first of all, most importantly, the reaction that you're dealing with, and the equation that you're dealing with is a redox reaction. Secondly, these reactions are often self-indicating, meaning you don't need other sources of indication such as an indicator or a pH meter or anything like that. Now, to show what each of these differences looks like in the context of redox stoichiometry, we're going to look at a couple of example problems, and I'll show you what the key differences are. In particular, redox stoichiometry is a big topic of interest for redox titrations. So what we're going to do is we're going to look at a couple of redox titrations and see how they differ from normal titrations. So a typical titration question would look like this. You've got potassium permanganate solution used to oxidize 10 ml of an iron 2 solution. What is the concentration of iron 2 ions? Now, with any titration question, you'd normally start by writing an equation. The difference here, the key difference, is that you need a redox equation, not a normal chemical equation. This can make things a little bit difficult, but the trick to it is to use what you know, use the knowns. And potassium permanganate is a good place to start. Potassium permanganate is KMnO4, and from past experiences you may be able to pick that potassium permanganate is a really good oxidizing agent. In particular, the MnO4 minus component of it is really good at oxidizing things. Now, if you're not sure what it does, or if you didn't know this, you could go to the electrochemical series and find its reaction, and that would tell you what it is. That's a good place to start. MnO4 minus, when it oxidizes, becomes Mn2 plus. Again, the electrochemical series will tell you that. You then go ahead and balance this as per normal. You put 4 H2O's over here. You then need 8 lots of H plus over there, and you need 5 electrons. And so there you have your equation balanced. Now, a handy thing to remember in this entire topic is your two most common reagents. One is MnO4 minus and the other is potassium dichromate, Cr2O72 minus. They're both very common components of redox titrations. Anyway, when you balance it out, you'll notice that it's gaining 5 electrons, which means it is an oxidant. And that kind of tells you what's happening to the other species. Fe2 plus is going to get oxidized. Yeah, if MnO4 minus is getting reduced, then Fe2 plus has to get oxidized. So the only way this would work is Fe2 plus became Fe3 plus E minus. You can again locate an Fe2 plus reaction from the electrochemical series, and this is the only reaction that would be compatible. And then the next thing you do is you use these two reactions and combine them together. And to do so, you'll have to multiply this bottom reaction by 5. Multiplying it by 5 gives you this, and then you can combine these two reactions together to get an overall equation. When you write it out, your overall equation looks a bit like this. The key thing from this equation is the ratio of MnO4 minus to Fe2 plus. It's a 1:5 ratio. As with any stoichiometry question, that molar ratio is super important. The next thing we've got to understand is the actual indication part of it. MnO4 minus is purple, and Mn2 plus is colorless. And this means that when you place MnO4 minus in a solution of Fe2 plus, you should get a color change. Now, the way we do this is we set up our burette with MnO4 minus, and as you can see, that's what's happening in the diagram here, diagram number 1. We set it up as follows, and then we dropwise keep adding a drop of MnO4 minus into our Fe2 plus solution in the conical flask. Now what will happen is every drop you add will actually change color. because every drop of MnO4 minus you add is reacting with the Fe2 plus. So it'll change to colorless, change to colorless, change to colorless, change to colorless, and then eventually you'll add one extra drop that will stay purple. And the reason it stays purple is because all of the Fe2 plus has now been used up. And that extra drop you've just added is staying purple because there's no more Fe2 plus left to convert it to Fe3 plus. And as a result, you now know you've reached your endpoint. That's when you stop your titration, and that's when you clock your volume. So the weird thing is, endpoint here is when it stays purple, whereas if it's still colorless, you're still going. Okay, so now our next bit is where we actually get to the titration part. So our volume of MnO4 minus was 0.015 liters or 15 mils. Concentration was 0.05. We can use this to find number of moles. Number of moles is of course 0.015 times 0.05. Then this should give you 0.00075 or 7.5 times 10 to the minus 4. Now the next thing we need to do is use these number of moles of MnO4 minus to find number of moles of Fe2 plus. That's what we do in a normal titration. In this case, once again, like a normal titration, we use our molar ratio. Our molar ratio here is 1 to 5. So what we do is we take our 0.00075 and divide it by 1 times it by 5. Yeah, because you have 5 times as much of the MnF of the Fe2 plus as you do the MnO4 minus. So you divide by 1 times by 5, and that gives you 0.00375 moles. And now finally, we're asked for concentration. Concentration equals number of moles over volume, so N on V. In this case, our N is 0.00375. Our volume in this case is 10 mils or 0.001. My apologies, it's 0.01. In any case, when you divide this, what you should get is your concentration. And your concentration in this case is 0.375 moles per liter. And that should be in 3 significant figures because your values are in 3 significant figures as well. That's your final answer. So please do as many of these questions as you can, and there are some questions in your activity books. The key thing to remember in redox stoichiometry is that you are dealing with a redox reaction and that often they are self-indicating. Thanks for listening.